Hello students, welcome to EPG Pathshala. I am Professor P03 from the University of Jammu. Today we are going to discuss about a module entitled High Temperature Solution Growth under paper Crystallography and Crystal Growth. Learning objectives. In this module we learn about a crystal growth technique known as Flux method of crystal growth. This type of growth is explained to be a high temperature solution growth. This method allows growth of crystals at temperatures well below the melting point of the material. Advantages and disadvantages of flux growth are described. The equipment involved in flux growth are described. The two growth procedures, namely growth by flux evaporation and growth by slow cooling, are described. Now, growth of flux. In general, the principles of high temperature solution growth are more or less similar to those of low temperature solution growth. The methods that are used in low temperature solution growth can also be used in high temperature solution growth, except the modifications that may be required because of different temperature regimes. Flux method is a high temperature solution growth method. Crystals are grown from pure melt provided the material to be crystallized is stable at its melting point. However, solution methods allow growth of crystals at temperatures well below the melting point. The distinction between pure melt growth and fluxed melt growth is that in case of the former, the solvent, that is the major component, freezes, whereas in the latter, it is the solute which crystallizes usually below its melting point, if it be assumed that it even has one. Flux melt growth is a method by which a wide range of crystals may be grown with the minimum equipment and information. Components of the material desired as single crystals, usually a simple or complex oxide or fluoride, are dissolved in flux or solvent. Crystal growth then proceeds at relatively low temperatures, often as much as 1000 degrees centigrade below the melting point of the solute. Flux melt growth is achieved by using any of the following two types of processes: growth by spontaneous nucleation and seeded growth. Advantages of flux growth. Most of the advantages of flux growth result from the fact that crystals are grown at temperatures below the melting point. The advantages are: number one, crystals are relatively free from thermal strain, and it is possible to grow good quality crystals. Number two, the container problem for refractory materials is avoided, e.g., MgO melts at 2800 degrees centigrade. At this temperature, the only suitable container is MgO powder. Usually, flux growth takes place at 1250 degrees centigrade, and so platinum container can be used. Number three, it is not possible to use pure melt growth of incongruently melting materials which decompose into another solid phase and or liquid at temperatures above their melting point. Number four, such materials which are volatile at the melting point may be grown by flux method at much lower temperatures. Number five, flux method of growth permits crystal growth of materials which undergo a solid state phase transition, resulting into severe strain or fracture as the growth occurs at a temperature below this transition. Number five, such complex oxides which may have volatile components and decompose just before the melting point cannot be grown from the molten phase. As for example, in the growth of GdVO4, one of the components used is V2O3. V2O3 is volatile. ROF, where R stands for rare earth, is the other component which loses RF3 at high temperatures. As such, it is not possible to grow such oxides from the molten phase. Growth by flux method avoids this problem and makes it possible to grow crystals of such complex materials. So, flux method of growth enables one to grow crystals of materials which become non-stoichiometric because of the loss of a volatile constituent. It is desirable to grow crystals of such materials which have very high vapor pressure at the melting point. Flux method is applicable to refractory materials which are technically difficult to grow as crystals from the melt because of crucible or furnace problem. Flux method yields faceted crystals as if they were grown in nature. The apparatus required is simple and within the scope of most of the laboratories. The flux method, however, suffers from some disadvantages. The major disadvantages of flux method are the following. Number one, the crystals grow in the presence of major impurity which comes from the solvent. To overcome this, one has to use means of slow growth rate so that capture of solvent inclusions by the growing crystal is avoided. Alternatively, one may also make choice of a suitable flux which may reduce this to a minimum. Flux method yields relatively small size of crystals. Equipment and other materials that are required for the growth of crystals by flux method include the following: crucibles, adequately ventilated muffle furnaces, thermocouples, temperature controllers and programmers, refractory muffles for flux evaporation, refractory bricks and means of shaping them as may be required, materials required for mixtures of solute and flux. Now the growth procedures. There are two growth procedures that may be followed for the growth of crystals from flux melt. Growth by flux evaporation, growth by slow cooling. Slow cooling process. The equipment for growth by fluxed melt technique using the process of slow cooling is typically of the type as shown in figure 28.1. Figure 28.1 is horizontal furnace with crucibles inside it for flux growth of materials by slow cooling method. Crucible made of platinum or rhodium, depending on maximum temperature to be attained, charged with the starting composition of appropriate stoichiometry, is placed in the seliminite, that is Al2SiO3 furnace muffle. It is preferable to keep lid over the crucible in order to safeguard the interior of the furnace from any attack by volatile toxic material. Sometimes it becomes necessary to weld lid with the crucible if there is any indication of the lid getting blown off during the experimental process. Tightly held lids with a pinhole are also sometimes used if the situation so demands. The composition of the charge includes well homogenized chemicals and flux components. It is then pressed into the crucible and placed in the furnace. The contents of the crucible are raised to a temperature of 1300 degrees centigrade or so and held at that temperature for a soaking period of about 12 to 24 hours. It is followed by slow and controlled cooling at the rate of 2 to 4 degrees centigrade per hour till about 800 degrees centigrade with the help of electronically controlled temperature programmers. After this, the cooling rate may be increased to about 100 degrees centigrade per hour till room temperature. The crystals are then separated from flux either by hammering or a special technique of hot pouring, which will be described later if required. The crystals may then be cleaned in 20% HNO3 if need be. The rate of growth V of a crystal of area capital A is determined by supersaturation. This in turn depends on the process used to produce the supersaturated state, which is an essential requirement for crystal growth. If the solution is cooled at a rate dt by dt, the growth rate V is given by V equal to V upon rho into A into dNE upon dt into dt upon dt. The crystal density rho and the slope dNE upon dt of the solubility curve are fixed by the system. The solution volume V is selected depending on the total mass of crystals required, and the area of the crystal faces will change as the crystals grow. According to this expression, the most important parameter is the growth rate dt by dt, which is directly responsible for the rate of mass deposition. Therefore, it is the most important factor in an experiment which will control the growth rate. In general, a constant cooling rate of about 1 degree centigrade per hour is most acceptable, provided it can be done in the background of experimental feasibility and convenience. The process of slow evaporation is not that popular as the slow cooling process as a method of producing crystals. It is, however, used only when compound formation occurs at low temperatures. As an example, we may consider the chemical reaction PbO plus TiO2 gives PbTiO3 at temperature T less than 1200 degree centigrade. So, TiO2 could be crystallized only by evaporation of PbO at temperature greater than 1200 degree centigrade. The growth rate is given by V equal to Ne upon rho A into dV by dt. It means that the growth rate depends on Ne and so obviously temperature T and on evaporation rate dV upon dt. Control of growth rate in this case is more difficult in practice than in case of slow cooling. However, the technique is to vary the size of the hole in an otherwise sealed crucible. During growth, the hole gets smaller because of deposition of solute that is transported in the vapor, and so the evaporation rate and hence the growth rate varies. There have been several innovations in the design of apparatus which have slightly improved the control over solvent evaporation. Advantages of flux evaporation. The advantages of growth by flux evaporation may be summarized as follows. Number 1. Growth of crystals occurs at higher temperature than with the slow cooling method. Number 2. Crystals having a small variation of solubility with temperature can be grown. Number 3. If the process of crystal growth is carried out to completion, almost cent% yield of the solid phase is achievable. Also, crystals free from adhered flux are obtainable. Number 4. In certain cases, large well-formed crystals are produced at the base of the crucible. Disadvantages of flux evaporation. There are certain disadvantages in growing crystals by flux evaporation as may be summarized here. Number 1. Nucleation at the melt surface may be excessive, which is likely to result in intergrown crystals. Number 2. Control over the growth process is lesser as compared to slow cooling method. The latter process of growth yields better quality crystals. Number 3. If the segregation coefficient between dopant present in the solvent and in the crystal differs from unity, there will be a greater concentration gradient in crystals grown by flux evaporation than by slow cooling. Number 4. Be it growth by slow cooling or evaporation of solvent, crystallization occurs by spontaneous nucleation in both cases. The growth procedure. The basic technique may best be explained by a description of the flux growth of a ruby crystal as perfected by Remika of the Bell Telephone Laboratory, USA. The experimental setup is shown in figure 28.2. The platinum crucible of 6-inch diameter and 10-inch depth is loaded with flux consisting of suitable amount of lead oxide and boron oxide, that is B2O3. To this is added appropriate quantity of aluminum oxide, that's Al2O3, and a small amount of chromium oxide, Cr2O3. The crucible, charged with the flux and constituent chemicals, is placed on a pedestal as shown in the figure in an electrically heated furnace. The pedestal is rotated 30 turns in one direction and 30 turns in the opposite direction to obtain uniform mixture of the molten contents of the crucible. The temperature of the furnace is raised to 1300 degrees centigrade. At this temperature, the aluminum oxide and chromium oxide get dissolved. After 6 hours, mixing is stopped and the temperature is lowered at a steady state of 4 degrees centigrade per hour for 8 days. At this stage, the furnace is shut off and the crucible is taken out. As the temperature passes 1240 degrees centigrade, on the way down, the solubility of ruby is exceeded and the crystals grow as the temperature is further reduced. To favor growth of crystals on the bottom rather than at the surface of the melt, top of crucible is kept 10 degrees centigrade hotter as compared to the temperature of the bottom by adjusting power of the heater. It has to be ensured that the temperature is kept constant, since a sudden drop would cause the production of small crystals rather than the dissolved few large ones. Another consequence of temperature fluctuations is the occurrence of inclusions of small amount of flux into the growing crystals, rendering them useless for optical studies and adversely affecting their beauty. The flux is removed from the grown crystals by dissolving the former in nitric acid, which neither affects rubies nor the crucible. Rhombohedral ruby crystals having size 1 by 4 inch across and large flat ruby plates up to 1 by 10 inch thick and several inches across have been obtained using this experimental setup at the Bell Laboratories, USA. In the initial stages of launching this study, choice of flux, one of the most important requirements of growth by high temperature solution method, is making choice of flux. For all solution growth techniques, one is required to find a suitable solvent. Two types of solvents are used in high temperature solution technique. One is liquid metals like gallium, indium, and tin, which are often used for the growth of semiconducting materials, whereas the other includes oxides and halides like PbO, PbF2, which are used for ionic materials. The solutions in oxide and halide solvents are called flux melts, which is because the solvents used are those which are used as fluxes in operations like welding, soldering, and brazing. A good flux should have the following properties. Number one, it should have a low melting point. Number two, it should be a good solvent, dissolving anywhere between 5 and 30 weight% of solute at the maximum temperature intended to be used. The solubility should decrease with temperature. Number three, it should not form a compound with solute nor a solid solution beyond a degree which depends on the proposed use of the crystal. It should be compatible with the material of which the crucible is made over the proposed temperature range. For growth by slow cooling method, it should be of low volatility. For a volatile flux, it is necessary to use lower temperature range, a faster rate of cooling which often results in the nucleation at the melt surface. Evaporation may be prevented if lids are welded to the crucibles, but this refinement is expensive and time consuming. It should be of low viscosity. Toxicity of flux should be low. The flux should be such as to be easily separable from the crystals. The supersaturation required to cause nucleation should be much larger than that required for growth of crystals. It helps in creation of only a few nuclei and growth of larger crystals. Example of some suitable solvents. It is given in the form of a table where some of the most frequently used solvents for the growth of some crystals are given. This is table number 28.1. Some suitable solvents for the growth of some materials. The material KNBO3, the solvent used is KF or KCl. The material GaFeO3, for which the solvent Bi2O3 plus B2O3 is used. For material Fe2O3, the solvent used is Na2B4O7. For the material BaFe2O4, Na2CO3 is used as a solvent. For material Al2O3, the solvent used is PbF2 plus B2O3. For BaTiO3 material, the solvent used is Bi2O3. For ZnO material, the solvent used is PbF2. For ZnS, the solvent used is ZnF2. For germanium, that is Ge, the solvent used is In or Sn plus Pb. For GaAs, that is gallium arsenide, The solvent used is gallium and Sn. For the material ZnTe, the solvent used is PbO plus B2O3 or PbO plus PbF2. For the material Y3Fe5O12, the solvent used is PbO plus PbF2 or BaO plus B2O3. For the materials of rare earth perovskites of the type RFeO3, where R is the rare earth representing Dy, HO, GD, TB, ER, YB, SM, LA, and Y. The solvent used is B2O3 plus PbO plus PbF2 plus PbO2. For the growth of RaLO3 crystals, where R represents GD, EU, SM, ND, LA, Y, PR, TB, DY, HO, and ER, the solvent used is PbF2, PbO plus PbO2 with B2O3 and MOO3 as additives. For the growth of RCRO3, where R represents Y, LA, GD, YB, the solvent used is PbF2, PbO2 plus B2O3 with B2O3 as additive. For the growth of LaBO3, that is lanthanum borate, the solvent used is PbO plus B2O3. For the growth of hexaferites of the type SrFe12O19, both pure as well as substituted with cobalt, titanium, and gallium and indium, the solvent used is Na2CO3. Separation of crystals from flux. Flux is often found to get adhered to the crystals and their separation from the crucible and or the grown crystals becomes essential. One method is to separate the crystals from the adhered flux by gentle hammering. If it does not work, one is required to undertake other means. Separation of crystals from flux is one of the most important steps in obtaining crystals. Franklin of the Crystal Growing Group at the Clarendon Lab, University of Oxford, has grown a large number of crystals using flux method. A lot of innovation has been done by the group regarding growth of crystals by this technique. One of the several innovative techniques concerns separation of grown crystals from flux. To prolong life of a crucible and separate crystals from flux without damaging them is to remove flux from the crucible while it is in a molten state. One way is to invert the crucible using long-handled tongs and then placing the same upside down on a refractory brick or a bed of alumina as shown in figure 28.3. The other technique is what is called as hot draining of flux as is shown in figure 28.4. The other method is to use a furnace in which there is a mechanism of inverting the crucible in the furnace itself. This arrangement is shown in figure 28.5. Now we shall discuss some examples of flux-grown crystals. Flux technique has been used for the growth of a large number of crystals, particularly those materials which are required to be grown at temperatures well below their melting points. These include a large number of materials which are very useful to electronic, magnetic, and optical industries. The materials generally are complex oxides or fluorides. The list is very long and one can search for the same in the literature. However, some typical examples may be given here. Growth of rare earth orthoferrites. The crystals of rare earth orthoferrites bearing composition RFeO3, where capital R is equal to Dy, HO, GD, TB, ER, YB, SM, LA, and Y, are grown using appropriate stoichiometric starting composition of R2O3 plus Fe2O3 with B2O3 plus PbO, PbF2, PbO2 as flux component. The composition is homogenized by vigorously mixing the same. The well-mixed composition is pressed into a platinum crucible and placed in the furnace, where it is held at a temperature of approximately 1300 degrees centigrade for a soaking period of 12 to 16 hours. It is then cooled at the rate of 2 degrees centigrade per hour till 800 degrees centigrade is reached. Thereafter, it is cooled at the rate of around 100 degrees centigrade per hour till room temperature. Well-faceted crystals are formed at the bottom and or walls of the crucibles. The crystals are separated from flux by gently hammering the crucible and then cleaned in 10 to 20% HNO3. Growth of rare earth orthochromites. The crystals of rare earth orthochromites bearing composition RCrO3, where capital R represents Y, LA, GD, YB, are grown using starting composition of R2O3 plus Cr2O3 with PbF2, PbO2, B2O3 as the flux component. The rest of the procedure is almost the same as in the above case. Growth of rare earth aluminates. The growth of rare earth aluminates bearing composition RaLO3, where R is equal to GD, EU, SM, ND, LA, Y, PR, TB, DY, HO, ER, are grown using starting composition of R2O3 and Al2O3 with flux component PbF2, PbO, PbO2 and B2O3 plus MoO3 as additives. The rest of the procedure is almost the same as in the above case. Growth of lanthanum borate. Lanthanum borate crystals are grown using La2O3 with flux component PbO and B2O3. The starting composition is pressed into a platinum crucible and then maintained at a soaking temperature of 1250 degrees centigrade for 15 hours. The cooling rate is maintained at 3 degrees centigrade per hour till 700 degrees centigrade, and thereafter faster cooling is done as in the above cases. Crystals in the form of platelets, tabular, and equidimensional are produced. Some of the crystals of LaBO3, which are approximately equidimensional and grown following the above procedure, are shown in figure 28.6. Growth of M-type hexaferrites. Growth of M-type hexaferrite crystals of the composition SrFe12O19, that is strontium hexaferrite, is achieved by taking strontium oxide and iron oxide, known as the ferrite composition, and sodium carbonate as flux. The ferrite and flux compositions are taken as 73.7% and 26.3% mole percent respectively and pressed into a platinum crucible, which is then placed in a vertical type furnace. The material is soaked at 1320 degrees centigrade for 24 hours under continuous oxygen flux and then allowed to cool at 4 degrees centigrade per hour till it attains a temperature of 800 degrees centigrade. Thereafter, it is allowed to cool at a slightly faster rate. Substituted hexaferides bearing the composition SR, XA, Y subscript B, Fe 12 minus A plus B, O19, where X and Y represent the substituting atoms, are grown following the same procedure as described above to investigate the effects of making substitutions in hexaferides. Let us now summarize of what we have discussed so far. Advantages and disadvantages of growth by flux evaporation are explained. Crystal growth setup as perfected by the Bell Telephone Laboratory USA for the growth of ruby crystals is discussed as an example for explaining the procedure adopted in this technique of crystal growth. Properties of good flux are identified. Suitable solvents for the growth of some specific crystals are given. Procedures involved in separating flux-grown crystals from adhered flux, including method of crucible inversion, hot draining technique, and inbuilt mechanism in the growth systems for inversion are described. Specific examples of crystals of flux merit growth, namely growth of rare earth orthoferides, growth of rare earth orthochromites, growth of rare earth aluminates, growth of lanthanum borate, and growth of pure and substituted M-type hexaferides are described. Thank you.